Hi everyone. In my previous video, I started multivariable optimization and explained unconstrained optimization problem. In this video, I am going to discuss about Lagrange multipliers and I will be explaining how to use Lagrange multipliers to solve optimization problems. Lagrange multipliers. In the real world, it is pretty common you need to perform some sort of constraint optimization problems. The only change is the addition of several constraints on the decision variables. We still will employ the 5-step method. So step 2 is to select the modeling approach. So we can use the method of Lagrange multipliers in step 2. Let me explain this. We have a function f x1 to xn. So we call this y. And here we assume that the constraints can be expressed in the form of k functional equations. We can write our constraints d1 x1 xn equals c1. Similarly, g2 up to gk x1 xn equals ck. So these are the constraints. Constraints. Our job is to optimize. Our job is to optimize the function y equal f x1 xn over the set S we can define as x1 to xn are the elements, then elements should be satisfied these constraints for all I equal 1 to k. Then we can write down the gradient of f equal lambda 1 gradient of g1 plus gradient of g2 so on lambda k gradient of gk. So this lambda 1 lambda k are the Lagrange multipliers. Lagrange multipliers. Here we assume gradient of g1 and g2 up to gk are linearly independent vectors. Then let me write down the Lagrange multiplier equations. So partial derivative of f with respect to x1 equal lambda 1 partial derivative of g with respect to this x1 up to the k partial derivative of gk with respect to x1 so on xn g1 xn with respect to xn lambda k partial derivative of gk with respect to partial derivative of, these are the Lagrange multiplier equations. Lagrange multiplier equations. We must solve the n Lagrange multiplier equations together with the k constraint equations. So let me write down again here g1 x1 xn c1 up to gk x1 xn ck. So we must solve the Lagrange multiplier equations together with these equations, k constraints for the variables, for the variables, for the variables x1 to xn and lambda 1 to lambda k. We must also check any exceptional points at which the gradient vectors, gradient vectors here, uh, these gradient vectors are not linearly independent. So let me explain an example. Maximize x plus 2y plus 3z over the set x squared plus y squared plus z squared equal 3. So this is a constraint of this problem. So we can write down function f x y z equal x plus 2y plus 3z. Then g function, here we do have only one, that is x squared plus y squared plus z squared. So then get the gradient of f and g. Gradient of f mean partial derivative of f with respect to x, partial derivative of f with respect to y, and with respect to z. So you can get 1 comma 2 comma 3. Then partial derivative of g, same thing, g with respect to x, g with respect to y, g with respect to z. So this equal 2x, 2y, 2z. So then we can make these two equal actually at the maximum point. Let me write down this. At the maximum point, we can say these two should be equal. If these two are equal, then look at here, and this are equal, that means these two must be equal. Therefore, these are the vectors. So this component, these two should be equal, and these two and these two. So we can write down 2x lambda. We have lambda over here. So 2x lambda equal 1, 2y lambda equal 2, 2z lambda equal 3. So from this 3, you can get the x values 1 over 2 lambda, and y value 1 over lambda and z value 3 over 2 lambda. Right. Now we can use the equation x square plus y square plus z square equal 3. So that is the constraint. So now plug the x, y, z values here, x, y, z values to this equation. Now we can write down 1 over 2 lambda to power 2 plus 1 over lambda to power 2 plus 3 over 2 lambda to power 2 equal 3. So solve for lambda. So lambda will be plus or minus 42 square root over 6.